Hello everyone, welcome to the webinar. This is Luboš Pirkl speaking. I would like to welcome you to the webinar where we would like to show you how to simulate an acoustic fan. Axial fan with acoustics. It's a new benchmark we would like to introduce to you today, and I hope we will show you everything you are looking for. So, yep. The webinar is being recorded, and the recording will be later made publicly available on our YouTube channel. There will be a Q&A session dedicated to your questions and our answers, so feel free to ask your questions, and we will do our best to answer all of them. The most relevant questions will be answered right away in the webinar, so feel free to ask anything about the workflow, about the simulation, about the pre-processing and post-processing, whatever that comes on your mind, and we will definitely do our best to answer your questions. You can ask anytime during the webinar. There is a special window you can find in the menu, so you can ask your question, and it's definitely for us a pleasure to answer them. Okay, so I think this could be it for the introduction, and I am sitting here with my colleague Radek Máca, and I will in the first part I will give general information about the company and our software, and pretty much some general information about simulations, and then my colleague Radek will tell about how to in fact hands-on session, how to run the simulations, and how to technically is the process realized. Okay, so let me go ahead. So this is yes, we're talking about the Axial fan, which is the benchmark we are going to present today. So basically, it's a new benchmark. So all the information is available on our website, and that's the topic. So it's about the Axial fan. So there are also other webinars we would like to invite you to. So yeah, there's a Kaplan turbine webinar, and also webinar about remote computing later this year, about centrifugal pumps, about external aerodynamics, and also about compressors, Francis turbine, wind turbines, and more other webinars are still to come. And yeah, I will start with a quick introduction. So CFD Support is the name of the company. CFD Support is company based or located in Czech Republic, in Prague. 15 years on the market. We have a lot of experience. We deal with engineering simulations. Basically, we can say we deal with CFD, FEA, FSI, with optimization, and with acoustics, which is today's webinar about. We have created a comprehensive simulation environment called TCAE, where the users can perform the simulations. So I'll just quickly mention that TCAE consists of software modules which serve for individual process parts, I would say. So there's a module for meshing, for CFD, for FEA, or for acoustics. There's also a module for optimization, and other modules are definitely still to come because we are developing in a very quick pace this environment according to modern trends. The beauty of TCAE is that it's extremely flexible, and the user can set up his original workflow depending on his or her skills, experience, resources, and the goals. So it's extremely flexible. It can be combined with commercial code. It can be combined with in-house codes. It can be combined with other open source codes. So it's definitely very flexible. It's unlimited. There are no limitations on number of users. There are no limitations on number of cores or hardware installations. There's only one license for the entire enterprise. and it allows the users to scale their resources to the fullest. There's a lot of flexibility involved also in licensing. TCAE is best for turbo machinery applications and for the external aerodynamics. It's not a general purpose code. It's focused on specific applications where it can be really great because it's focused. It's not aiming on everything. It's actually the aim is very narrow, and it allows TCAE to be accurate, and it's well automated. It can be well automated, and it is well automated. So it's always up to the user. We always leave up to the user how much to deal with the technical details or not at all. So it's both. It can be used both as a black box, or it can be used as a totally high-end software where all the options are open, and where all the details are open, because it's very transparent. There are a lot of benchmarks and tutorials available, so the users can directly use the benchmarks we did in the past. They can use tutorials which are ready for the tests, and they can play around with tutorials which are similar to their goals. We have also good technical support, because we believe that the software is only one part of the problem. The next part is to know how to use it. So it's important. The technical support is definitely extremely important part of the game. TCAE is ready to be used remotely. It can be used in a unique client server option, or it can be used directly on laptop, desktop. It can be used on a cluster or in the cloud. You can use it remotely from home or in Windows or in Linux. There are definitely a lot of options how to use it. It's extremely flexible also in this way of usage. TCAE is based on open source, so there are many open source pieces inside TCAE, and on top of these open source pieces, we have spent more than 40 many years of development. So there is definitely a huge value, because a lot of time and effort has been spent on this to be able to deliver this. So the current TCAE version is 24.03. So anyone is welcome to get involved. Okay, so this brings me to the case we want to present today. As I mentioned, there's a new tutorial and benchmark where we show how to use TCAE for axial fans, basically. And this case is specific because we use it for benchmarking our workflow also for the acoustics. So the acoustic module together with CFD module are employed, and the case is relatively comprehensive and relatively broad, because it's and heavy, because the CFD techniques are used, and based on the well-resolved CFD results, we can use also the acoustics to evaluate the acoustic properties of the case. What's very important to say right in the beginning, that acoustics it definitely brings a lot of new complexity to the case. So first, you should be pretty much sure that your CFD results are really good, that they are reliable, and they fit I would say at least your expectations, and maybe some other data. And then on top of that, you can build another acoustics level, because acoustics definitely brings another level of complexity to what is already pretty much complex. So you should be aware of this before you start doing acoustic simulations. And when I'll be talking about the case we will present to you today, we liked very much an article which is created by researchers from Austria, from Vienna, and I think from Graz University. This is the reference we have seen that there's the article from Mr. Schoder and others. They definitely spent a lot of time. They had some measurement facility, and the even more details are described in this article. So I definitely recommend this article, and our work is based on this article. So there's a I would say measurement facility which can measure the properties and also acoustic properties of the fan, and this is what we have simulated in this case. Yeah, so basically it's an axial fan with a wall in the middle, and I would say with a motor from there are two chambers divided by a wall, and the motor is rotating with the fan, and we are measuring and simulating stuff. What's going on here? Yeah, so this is the acoustic benchmark what we have created. There's so much more information available on our website, so feel free to visit our website, cfdsupport.com, where you can find the case study with all the technical details. So you do not need to remember everything from this webinar. This webinar goal is definitely to show you the principles, to give you a good impression what's on the table. But of course, all the details, all the numbers and parameters, you can find them on our website. There's also a PDF which you can download and look at all the details in the PDF. And you can definitely always contact us and ask for the details, and we will be as much transparent as possible and let you know all the details if you like. And of course, you can try it yourself. You can ask the trial version of TCAE, and you can load this tutorial and try the simulation yourself and give it a chance if you like. Okay, I think this is the time that we will switch here with the presentation, and I will ask my colleague Radek, who will continue, who will go ahead with it. So give us a second.
Hello. Thank you, Luboš. So we are literally switching the chairs today at the same computers. So therefore, the switching was not smooth as usual. So let me introduce you the case live, and I will show you the workflow from beginning, and mainly we will focus on a TCAE module. So first of all, as Luboš mentioned, all the details about the case you will find on our web pages in the case study section. And here the first case to be viewed is this Axial fan acoustic benchmark. And for those who watch our previous webinars, and our previous webinar was on axial fan optimization, and basically the geometry and the topology of the flow domain was very similar to the acoustics benchmark case. So this axial fan optimization and basically the standard CFD simulation for axial fan is the first point or starting point to have the TCAE, the acoustic simulation. So let me just introduce this case. So as my colleague mentioned, all the details are presented here. You can find here the PDF report, the acoustic simulation report. So maybe we will refer to this later during this webinar. And by the way, if you go really to the bottom of this case, let me scroll down. So at the end, at the bottom of this page, you can also download this case, this project, and try by your own or analyze it by your own with our software. So let me go for the case. So now I will open it. So let me go to our folder today, which is the webinars Axial Fun Acoustic Benchmark. So let me open the project in TCAE. So the whole workflow consists of several steps as usual. So first of all, you need to have the geometry. So to have the prepared STLs for mesh generation, or to have the simulation ready mesh in external format to be loaded. Then the next step is to prepare the CFD simulation, so all the parameters which are relevant to your future purposes, which is the acoustic benchmark. So set the fluid properties, set the boundary conditions, simulation parameters, etc. Then if the CFD simulation is perfect and you are fine with all the other details, you can then go to setting up the acoustics module. So let's wait for loading the project. Perfect. Now we can see it here. So as Lubos mentioned in one of the last slides, the acoustic brings another level of complexity to the whole workflow. So the meshing has to be perfect, the CFD simulation has to be perfect, everything has to be prepared for the acoustics, so all the parameters like mesh refinement, the proper turbulence model, boundary condition, but all these parameters has to be perfect before you start going for the acoustics. So let me quickly introduce the topology. So as I already mentioned, you can see the same topology also for the previous webinars for the Axial Fun optimization. So the topology is the same. So we have three components, three regions: the inlet room, we can call it, the outlet room, and the rotating part itself. So when I make a slide just to see the contours of the domain, so let me apply this just to see the contours. So we have the red domain, which is the inlet domain. So component 1 is created by the inlet parts. Then we have the rotor part. So basically the cylinder, which includes our Axial Fun geometry, and the outlet room part, we can call it. So here we need to somehow focus on the mesh refinement, because for the acoustics we really need to have the refined mesh in the neighborhood of our object of interest, and also to capture all the details about the flow. So we need to have a nice refinement also, mainly in the outlet area, but also in front of in the section part before the rotor. So as usual, we set the standard meshing parameters. So we have a little bit rougher mesh in the inside and the outside room. Then we have some kind of cylindrical refinement to refine just the region in the suction part, and for the component 3, which is the outlet room, we can call it, we have another refinement region just to refine gradually the mesh in the outflow area. And of course we have the rotating region with a much finer mesh, so to have a nice resolution for the CFD simulation and for the final results. So all to capture all the details about the flow, which creates then the acoustic sources. All the other parameters are, let's say, so this is the meshing. For the CFD simulation, you set as a standard CFD simulation, so standard fluid properties. We need to have it compressible to come with all the effects, the physics which influences the acoustics. For the turbulence, we typically go for some hybrid models, some kind of DES models. Therefore, we need to have a fine refinement for the mesh. All the other, let's say, parameters are similar to standard transient simulation. So we have a transient solver, which is initialized by the steady state solution to speed up the convergence for the transient solver. So we have here steady state part, then we have transient part. So here we simulated 10 full revolutions because we are starting from a steady state results, so we don't need to simulate as many revolutions as for the simulation just with the transient run. So for the solver, here are the standard parameters. Time stepping, we have just really small time step to capture all the frequencies we need. Numerical order second, which is important to have the good accuracy of the results. Here the most important part, which is connected directly to the acoustics. So here in the runtime evaluated quantities, here you ask to write the acoustic data. So it's not, the acoustic is not simulated runtime. So first the acoustic data are gathered during the simulation, and after the CFD simulation, you can play with the acoustics. These have a benefit of playing with the acoustic parameters later, and you don't need to recompute anytime if you ask for new frequencies or whatever. So first the CFD simulation is run, all the acoustic data are stored on the disk, and then you can play with the acoustic analysis. So this is a huge benefit that you don't need to recompute the simulation, which is pretty demanding, and it takes usually days to weeks to compute high resolution mesh for longer time to be simulated. So this is important feature, that everything is gathered. It takes some storage, of course, but you don't need to spend time for recomputing the simulation again and again, and if you need to have some new parameters with in the acoustic part. So here we start to gather all the acoustic data from beginning until the end. The right interval means that every time step, so it's connected to the time step of the solver. So every time step, the data will be stored. Data format is standard binary format, but we are implementing other formats like some kind of compressed one and etc. to save some place on your disks. Acoustic surface. So here for this type of simulation, the acoustic surface is directly the patch itself. So all the acoustic analysis are then implemented in the way that counts with the rotating surfaces, so everything is done properly. Or for some application, you can ask for the external STL, and then some kind of general shape, general surface can be used to store the acoustic data. Sometimes it is used some STL or a set which amongst the object of interest for volumetric sources, but in this case we use directly CFD patches, and then you can ask which CFD patches are used. Then this source patches can be visualized afterwards in the TCAE module when it's set. So if I, for example, get rid of the source geometry, and here we can see the source surface for the acoustics. So it's just for visualization purposes. So for this surfaces, all the data for the acoustic, like density, pressure, will be stored, and then the acoustic module can use them to do the acoustic analysis. All right, so let's go back to the CFD module. So you are here in the runtime evaluated quantities. So we have these patches, and basically that's all what you need to set to have the data for acoustic analysis. So all the other parts is the same. You can ask for other probes to have better information about the CFD simulation itself and about the CFD parameters. Here we don't need any convergent check because we would like to simulate the whole span of time until the n time, so full 10 revolutions. What is important here, inlet outer boundary conditions. So we are simulating the fan at some specific conditions. I think there's something close to the best efficiency point for this axial fan. So standard boundary conditions, walls, interface conditions, everything is as a standard simulation, including the report and all the other parameters for TCFD module. Okay, so whenever this is done, you can go for the acoustic module. So even you haven't simulated acoustics, but you have prepared the data. So after the simulation, CFD simulation, you can apply the acoustic module and play with the setup of the acoustics. So it's an acoustic analogy. So it processes the data which are needed for the acoustic analysis, and then here you just set how to process the data and how to evaluate and how to perform the acoustic analogy. So here you said what is the source, because we can use directly the source from the CFD simulation, or if you have some old simulation, you can use the external data to locate the data of some kind of previous simulation and have just standalone TCAE module, which will be using the external data, typically from previous simulations. Because we have chosen the CFD simulation, so we directly see the sources from the TCFD module. Then we can play, what we can set here is the custom time range. So typically for some kind of simulation, we would like to skip the first part of the simulation because it's just initializing, and then we would like to start trigger or use the data for the acoustic analysis for some given time frame, typically after several revolutions. So here we will, or in this example, we gather all the information from the whole transient simulation. Then the important part are observers, because we do acoustic analogy. So the observer is a point to which the signal from the source is propagating, and then in that source the acoustic, not acoustic source, but the acoustic itself is evaluated, and then in the final report we will see all the acoustic data to the given observer. And then there is new feature, I think it's for the last observer group point. You can use the circular distribution, which is used to have this circular data plots, which you can also view in this example. So these kind of plots, polar plots it's called. So typically you choose some distribution of the points among your object, and for each point the given frequency is evaluated, and then you can plot it as a polar plot. So for this purpose, this circular distribution is available, and you just define the circle in the given plane and how many points should be created, and each point then creates new observer for which the acoustic analogy is performed. So you can play with as many observer groups and observer points as you need for your analysis. The next section, how to evaluate the data, are in the probes. So it's directly the point on a surface where some specific data are evaluated, like the pressure, acoustic pressure is evaluated, and some kind advanced fields to see how the signal propagates to the given points, or to do some deeper analysis. Physical constant connected to your simulation. So the reference sound pressure level, so 0 decibel pressure level, and speed of sound for given environment. Then the part for signal processing. So how here some kind of low and high frequency filters are applied to filter out some artificial signals or unwanted signals from the source signal, and the processing for the fast Fourier transform, some kind of hand signal window processing to have better frequency analysis. All right, so I think this is clear. And the last one, the report. So here again, you can adjust the report to your needs. So which section you would like to see in the final report, what units are your preferable, and here you can ask for the frequencies to be evaluated for the circle plots. So there are some kind of a list of the frequencies you can ask for, and then basically for those frequencies you can see these polar plots. Right, I think it's clear. And additional data files. So if you compare the data to your experiments or to an external data source, or to compare several benchmarks, you can add some kind of CSV files for the results, previous results, or the experiments, which then appears also in the report as a comparisons. So maybe I can go to the up on the page. Here's the slide bar, and if you visualize the acoustic reports, then basically what you can see are these power spectral density graphs with compared values, which you basically define here. So which brings me directly to the report. So in a standard report, you see again, so it's very similar to the CFD, TCFD report or TFEA report. So you can see some kind of simulation statistics, observer summary, so some kind of overall sound pressure level, some integral value for the magnitude of the sound, and some recapitulation for the observer positions. Here's some kind of sound reconstruction. I think you can't hear it on your side when I play it, but you can go here and try just to see some kind of reconstruction of the sound. So it's very, very interesting. Then for each observer, you can see how the source signal looks like. So per each observer, you can see the signal which comes to the given observer, and on the right side here you can see the filtered signal after these low high frequency filters. So this is basically the signal from which the fast Fourier transform is made, or is done, is applied on, and then from the signal these sound pressure level or power spectral density is evaluated. So again, you can list all the observers you have defined. You can compare it to with the source data. So depend what was the original observer for the experiment, for example, and the other benchmarks. So you can nicely compare it and play with. The same for sound pressure level per observer. So you can here you have the original signal and then some signal which is transformed to the third and octave band. And last but not least, we have these polar plots. So for all the frequency you have asked in the report or in the setup of TCAE, you can visualize these polar plots for some kind of advanced analysis. All right, and I think I'm almost at the end about the acoustic. So as you can see, the setup of the acoustic analysis itself is pretty straightforward compared to the CFD or meshing sections. Is you can say this piece of cake from the point of view of just setting the parameters, but as we already mentioned, the complexity which is applied on the CFD simulation and the meshing itself is extremely high compared to a standard CFD simulation when you're just looking on the integral values of the efficiency and powers. or other quantities. So here you can really focus and really pay attention to the CFD setup and the meshing parameters, which affects the acoustic analysis itself significantly. So you can really has to be really expert on the first parts before you go for the acoustic part. Okay, so if we go back to the report or to this case page, last but not least, which is available in the newest version or the beta version of TCAE, we have also developed these surface frequency and surface frequency phase and intensity or amplitude surface plots, which is really nice to understand what is happening on the blades from the point of acoustics, how the phases are gathered, or how the source of the sound are basically built on your source areas. So these plots are available automatically from the next version or upcoming version, and these can be also analyzed and plotted automatically after the acoustic analysis is done. And of course, for some kind of advanced visualization, you can store also the CFD data during the simulation and then play with the visualization of the turbulence connected fields, pressure fluctuations, or whatever you need to visualize. All right, so from my side, I think I have shown what I needed, and maybe now I will let Luboš to conclude, and maybe we go directly to the Q&A section or Q&A part of this webinar. So I just give the headphones to Luboš.
Yes, thank you, Radek. Yes, today we have special conditions here because we had some technical problems that we learned just a couple of minutes before the webinar starts. So we believe that our audience will understand, and let's go ahead. So I'll go back to the presentation. Right? Yeah, Radek, that's great. So I hope the audience still can hear us. They can see the presentation. So now it's time for the Q&A. So we would like you to ask the questions, and we will definitely do our best to answer some of them, which we find relevant and also yeah, important for the others. And you can be sure that if there is something too specific or too detailed to your case, we will talk about it, yeah, individually via email. So feel free to ask. What we have here. We have received some questions in advance, so I guess we can start with them. The question is, Radek, would you like to answer them, or shall I? Okay. Okay. Okay.
So let's start with the first.
Yes. Yes. Okay. So I will. Yeah. Yeah. Today it's special, so I will just say it. We received a question about yeah. There was. I hope I can remember them. So there was a question if we can use periodic boundary conditions. For example, if you would like to simulate just a single blade, not the whole wheel or the impeller, but just a single blade. So definitely it's possible, and in fact we think it in a result for productive simulations it will be the point, and certainly there will be used just a single blade for various reasons, especially the time, because the simulation time for this case was a couple of days on I would say good personal computer. So I'm sure that the users, because the time is everything basically for all the simulations and all the engineering processes. So definitely it would be a choice to use the periodicity. Of course, it's a kind of simplifications, yeah, but yeah, for sure, periodic simulations are at stake. We do it for some in projects for some other clients in consultancy business. So yes, it's definitely for productive simulations an option and the case. Yeah, there was another question which is pretty relevant. So it was whether the interface between the rotor and static parts can't let's say influence these acoustics properties, because we know that sometimes it may happen that the interface produces various oscillations. So again, it's a good question. Radek is telling me yes, we had this case in our development part, and I hope you can still see my screen, that we reflected this problem a couple of years ago actually, and we did a lot of tests that there were oscillations due to the I would say rough or let's say not a very nice mesh at the interface between the impeller and the static parts. For example, here you can see that for actually centrifugal rotation machines that we made a sensitivity study, and with fine interface we were able to mitigate, I would say, this effect. And for axial machines the effect was so much smaller. So this, for example, for this axial fan, this effect of oscillating interface is not a big deal at all, but because it can be solved by a fine resolution of the interface, which was confirmed in the internal study we did here in the past. So this is just one question of what we received for this specific case of this axial fan. We didn't do this sensitivity tests because we didn't focus specifically on this. We just received this question, so we are answering it. Hopefully we are here on the safe side, because we are, as Radek mentioned, we are developing we are building the acoustic sources just out of the blades, and the blades are the main source of the noise. So hopefully it's another reason why the interface oscillation might not have a major effect. Yep. So it's this, and we have. Let's take a look. Yeah. So there is another question. Yeah, there was another question about time varying boundary conditions. So it's actually quite a good question, but I don't know if we are going to if we are fully capable to answer it right away. Yes. Okay. So yes. So there are a lot of options we can use. It's possible because we have options to if not directly in the graphical interface, we can use scripts that change the boundary conditions at the inlet, for example, to something what we call time varying boundary conditions for whatever quantities we select. So there are a lot of options that can be used even for, of course, I'm talking here about transient simulations, but we can still change what's at the inlet or at the outlet during the simulation time. So there are a lot of possibilities regarding this. Yes, another question is about the Y plus and the number of boundary layers at the surface. So we, yes. I hope the answer is directly on the website. So let me see. I think we have something like 10 inflation layers on the impeller, but we can take a look if whether the information is here. Yes. So yeah, the number of inflation layer added on the mesh is 10, and the Y plus is varying from 0.07 or to 35 somewhere, because it's a local quantity, right? So it's not just a number. So the minimal is very small, the maximal is bigger, hopefully in the somewhere where it doesn't take any major effect. So it's this, and another question is about is it direct acoustic or FWH? Yes, so it's the analogy, right? So we use the analogy. I guess Radek mentioned it, but still I can say it. Yes, it's is the analogy Ffowcs Williams-Hawkings, which is used in the workflow. I think this is good enough at the moment. Okay, and I have to say I can't see any more questions, so this brings me to conclusion of the webinar. So basically I'll conclude here. So thank you for your patience. Thank you for staying with us. It's a pleasure for us to talk to you and to show you what we have. So yeah, I would like to thank you for your attention, and feel free to get back to us. We will gladly help. So stay in touch with us, and this is gonna be it for now. So thank you. Bye bye.